So, dear students, welcome back. We have reached in the book section 3.4 in this lecture, and that is about the quadratic variation of Brownian motion. So we have seen quadratic variation, of course, before for the symmetric random walk, which was a discrete process, and now we will generalize this to a continuous process. This will turn out to be very important when we're dealing with Ito calculus in chapter 4 and with stochastic integration. But first, let's do some general notions. Well, as we have seen, Wt, that is the Brownian motion, t greater or equal to 0, it has continuous paths. So for each fixed event, little omega in the event space, big omega, the function mapping t to Wt is a continuous function in t. And now we have seen several continuous functions before in calculus. If you think of continuous functions, we often think of functions like this, right? Functions that are smooth, that have continuous derivatives, or at least the first derivative, which is continuous. But now when we're dealing with Brownian motion, we recall that we have a zigzag function, a function with a lot of peaks, sharp peaks, and the derivative does not exist. Still, we want to say something about functions like this. We want to measure the smoothness. We want to say something about the peaky behavior in small intervals. And for that, one uses typically the concept quadratic variation. Now, let me first say something about the symmetric random walk that we have seen before. We denoted that by m sub n greater or equal to 0. And for that, we have defined the quadratic variation as follows. We have written it as m in brackets. So the quadratic variation of m after k steps. We had a discrete process, so we had a time step, k, a time step related to k. And after k steps, we defined the quadratic variation as the sum of j running from 1 to k of the increments mj minus 1 squared. So it is the quadratic variation, the sum of square increments. It is the sum of square increments. So this is a stochastic process in principle. The quadratic variation is a stochastic process, but in this case, for m, the quadratic variation for m, that is a constant that we have seen a few lessons back. Now for Brownian motion, we are dealing with a continuous process, so there is no time step. And we have to generalize the concept of quadratic variation to those processes. Now that is done as follows. Here's the definition of quadratic variation, and for that we use a general function f. So formally, the quadratic variation is defined as follows. Let's have a function f that runs, that is defined in 0t, and it maps onto R. So that is a function. Now the quadratic variation of f is defined as follows. We write it again with the square brackets. The quadratic variation of f with a subscript t running to t, or sometimes we write it with the t in brackets. That is the supremum over partitions. A partition being, if we have our interval and we have our t0, t1, t2, t2, up until tn. Yeah, we have a lot of points, and we can make this partition finer and finer and finer. So our partition is like this, and of course we can think of a coarse partition and we can think of a finer partition. Calligraphed P is the partition. Now the quadratic variation is defined as the supremum over the partitions of the sum, j is running from 1 to n, of again the difference, f defined at ti plus 1 minus f defined at ti squared. So again, it is the sum of the sum of squared differences. And now if we define a subset of, an increase in subset of partitions with increasing number of points, so P1 is contained in P2, is contained in P3, etc. So if we define those, and which then means that each of these has an increasing number of grid points, these points, and therefore a smaller and smaller size of the partition. So the difference, the distance between two time points is getting smaller and smaller. And the amount in P, the size of P, we say it's the supremum of J between 0 and n-1 of this distance. This distance, so this, the size of P is related to the smallest distance, basically, I'd say the biggest distance here, Tj plus 1 minus Tj, so the step size. Now we can define the quadratic variation as the limit of this step size, this partition size, size of the partition going to 0. So the number of points going to infinity, if you wish, the size of the interval going, of the supremum of the intervals going to 0, of the sum, I is 1 to the number of points in that partition, we call it Mn, and therefore we have in total Mn minus 1 here, so it's the sum I runs from 0 to Mn minus 1, the number of points in that partition, of again f at ti plus 1 minus f at t squared. That is the definition of the quadratic variation of a function. So we can generalize that to Brownian motion, right? And then we can look at properties, quadratic variation properties of Brownian motion. Now, an important remark is that any continuously differentiable function has 0 quadratic variation. And how can we see that? We can see that with the help of the mean value theorem. So this is a consequence of the mean value theorem. And let me remind you about the mean value theorem. The mean value theorem tells you that there is always a, say, a Tj star in an interval Tj, Tj plus 1, such that the difference between two function values, f at Tj minus f at Tj, that can be written as f prime, the first derivative at that point Tj star, times the distance Tj plus 1 minus Tj. You may remember this mean value theorem. And if and we are going to use that here in order to prove that any continuously differentiable function has 0 quadratic variation. So let's write it out. What do we have here? This is the quadratic variation. First, the sum j is running from 0 to the number of points in the partition. F Tj plus 1 minus ftj squared. And with the mean value theorem, we can rewrite this as, this is a square, of course, so we can rewrite this as the first derivative, f prime at this intermediate point, t star j squared, times the interval tj plus 1 minus tj squared, right? This is now what we have found with the help of the mean value theorem. Now here we take one of these instances out, one of these intervals out, tj plus 1 minus tj, we take it out, and that implies that this function is less or equal to the partition. See that this is the partition. We take the maximum out. So then this is less or equal to the partition, size of the partition, times this sum. J is running from 0 to mn minus 1 of this first derivative squared times this interval, tj plus 1 minus tj. Now you see here, in fact, what we see here, a sum of this function times this interval, that is in fact a Riemann sum. If you see that, you recognize this is a Riemann sum. It's a Riemann sum for the continuous function f prime squared. Yeah, it is f prime squared evaluated at some point in the interval times the length of the interval. Yeah, so that is a Riemann sum. And we know that a Riemann sum converges to an integral when we take the partition smaller and smaller. So the last part is a Riemann sum for the continuous function, and therefore we can also say, of course, this is something square, a sum of squares, so it is at least 0, so it's greater or equal to 0. The quadratic variation of f is greater or equal to 0, and that is by definition in limit, the limit of the size of the partition going to 0, and therefore the number of points going to infinity of the sum j is 0 to m minus 1 of ft(i) plus 1 minus ft(i) squared. Now we take that limit, and in the limit we see that this converges to an integral. This will be an integral value. And when this partition goes to 0, this first term will go to 0, this will go to 0, this will go to an integral, right? An integral of f prime x dx squared, sorry. And it's multiplied by 0, so that is 0. So looking at left and right hand side, we see that the quadratic variation of a sufficiently smooth, of a continuously differentiable function is equal to 0. Now the question immediately is, what will be the quadratic variation of a Brownian motion? Now we will prove that the quadratic variation of a Brownian motion on 0t is equal to t. So it's not equal to 0, it is equal to the size of the time of the time axis of the final time. It's equal to capital T. Let's first start with the definition. The definition of quadratic variation of a Brownian motion, Wt, where t is greater or equal to 0, that is given by, in fact, the same. It's the square brackets of w, and then we write this t either in brackets or as a subscript. And here we explicitly write the omega just to look at the definition. But typically we omit the writing of the omega. That is in limit the partition going to 0. Of the sum, j is running from 0 to the number of points in the partition of w at tj plus 1 minus w at tj. Of course, it's a random variable, and then squared. And again, we have a sum of finer and finer partitions where then the size of the partition gets smaller and smaller and smaller. This is the formal definition. The formal definition that we will work with. So let's do quadratic variation and apply it to Brownian motion. So again, we make this partition, Pn, T0 is equal to 0, and it runs all the way, and then we have smaller than T1, smaller than T2, etc., to Tn, which is equal to capital T. That's a partition of the interval 0t, and we set this Q of Pn, we define that as the sum, I runs from 0 to n, of the difference of the increments of Brownian motion. WTi plus 1 minus WTi squared. And again, note that this is a random variable. So the quadratic variation of W at time t is given by this expression, the square bracket of W at time t, and that is then the supremum over this partition of this Q of P. Yeah. And again, because it's difficult to work with supremum, we say in the limit, this is the limit, the size of Pn, the size of the partition going to 0 of QPn. That is what we are looking for. That is the definition of the quadratic variation of a Brownian motion. Now there's a theorem, and the theorem is let W be a Brownian motion, then the quadratic variation of Brownian motion up to time t is equal to t, almost surely for all t. And the proof can be found in the book. The proof is a weak convergence in L2, and hence in probability, that is given in the book. And we will do it a little bit differently here. And we also provide yet another proof after the one that I will be discussing, and that one will go a bit faster, but you can read that back in the slides that of course will be provided again. So let me first remark two things about this convergence. Convergence in L2, essentially that means that means that in the limit of the partition going to 0, in expectation, the distance or the difference between this Q of calligraphed Pn minus T squared, because it is in L2, that expected value is equal to 0. Where again, this Q of Pn, remember that is the sum of J running from 0 to the number of points in that partition times the square of the differences, WTJ plus 1 minus WTJ squared. And the other one is convergence almost surely convergence, and that is simply defined as the probability of an event little omega in big omega that in limit with the partition going to 0, Q Pn omega is equal to T, that is equal to 1, that the probability that this is equal to T is equal to 1. And that is the almost surely convergence as it is typically defined. Okay, let's remember what we would like to prove. We would like to prove the L2 convergence of quadratic variation. So the aim is really to show that in the limit where the mesh size Pn goes to 0, the mesh gets finer and finer, number of points increase, and then the step length gets smaller and smaller. In this limit, the expected value of Q of Pn minus T squared is equal to 0, right? Squared, because we have L2 convergence. And in expectation, where this calligraphed Pn is a time partition of time, T0 is equal to 0, is less than T1, etc., less than Tmn, and Mn, these are the number of points that are in this partition. And Tmn is equal to the final time, capital T. Now QPn here, that is as follows. So QPn, that is the sum. J runs from 0 to this number of points minus 1. WTJ plus 1 minus WTJ squared. That is the definition of QPn from the previous slides. And T we can also write, capital T we can also write a little differently. We can write that as the sum, J runs from 0 to Mn minus 1 of Tj minus T. This looks a little bit awkward, right? But you see here we have a telescoping sum. What we add for one index, we subtract for the other index. And in the end, only the final point results. The first point minus the last point, the very first point minus the very last point results. So this is just a different way of writing capital T. Now, the term in the expectation sign here, QPN minus T, in this writing this out in detail with these expressions here gives us a sum. J runs from 0 to mn minus 1 of this first term, w at tj plus 1 minus w at tj squared, minus this second term. The t here is this, right? So in total, and we will name this, we will give this a name, we give this the name I sub j. So what we see here is I sub j squared, right? So each individual term is I sub j. So therefore QPN minus T is in fact a sum of the ij's here, yeah, I sub j's. And note that these I0, I1 up to IMN minus 1, note that these are independent and normally distributed random variables. We look at the increments here, right? And we have for I0, for J0, for J1, etc. We have one of those. Independent, normally distributed. All right, first thing that we see is that the expected value of this ij, the expected value is a linear operator. So the expected value of ij is the expectation of the first part in the expression, expectation of w tj plus 1 minus w tj squared, minus the expected value in this second expression, the expected value of tj plus 1 minus tj. Well, both of them we have seen already, of course. This one, these are these increments squared. So in fact, this is the variance, right? This is equal to the variance. Remember that the expected value of the w tj's and the increments were 0. We had that in the definition of Brownian motion. Yes, the increments were normally distributed with mean 0 and variance t minus tj plus 1 minus tj. So in total, this complete expression is t, let me see if I can write it a bit nicer. That is tj plus 1 minus tj. And of course, this second expression, well, this is just a deterministic quantity. So there's the expectation of a deterministic quantity is just the quantity itself. So this is just t plus 1 minus tj. And in total, the expected value of each I sub j is equal to 0. Now let's look at the second moment. The second moment, because that is in fact what we are looking at. If we look back, that is in fact what we are looking at if we are looking at this expression over here, right? That is the expected value of I, a sum of I sub j squared. So let's look at the expected value of I sub j squared. Well, let's write it out. So I sub j, remember, it looks like this. It looks like this. And we are going to square this. So that means we are squaring this term, making it to the power 4. We're squaring this term, making it a square. And we have the cross product, minus 2 times this term times this term. So writing that out, you'll see here, it is the expected value of this increment to the power 4 minus the cross term, minus 2 times this increment squared times tj plus 1 minus tj, plus the last term, tj plus 1 minus tj squared, right? This is the expression just written out. Now, again, The expectation operator is linear, so we can look at all the individual terms. Moreover, this time increment is just deterministic, so we can take it out of the expectation operator, and the expected value of this deterministic quantity is just a deterministic quantity. So we end up with the expected value of the increment to the power 4 minus 2 tj plus 1 minus tj times the expectation of the increment squared plus this term here. Now this fourth order term, that is a little difficult, but we know that these increments are normally distributed with a mean and a variance. And we also know that if x is normally distributed with a specific mean 0 and a specific variance, sigma square, then the expectation of x to the power 4 is in fact 3 times sigma to the power 4. So it's 3 times the variance squared, right? Because the variance is sigma square, and to the power 4, that is the variance squared. This can be found by just writing it out, by just doing calculus and looking at the integral that defines the fourth moment. So when we're using that for this one, we end up with 3 times tj plus 1 minus tj squared. Because remember, the variance was just tj plus 1 minus tj, and we have the variance squared here. So that is this one. This term over here, well, this is again that second moment that we have seen before. That is tj plus 1 minus tj. So in total, this is minus 2 tj plus 1 minus tj squared. This term times this term. And this term just remains, so it's plus that term, tj plus 1 minus tj squared. 3 times this expression minus 2 times this expression plus this expression gives us finally 2 times tj plus 1 minus tj squared. Right? And again, notice that the variance of ij, the variance of the individual ij's, that is equal to the expectation of ij squared, because the other part of the variance minus the expected value of ij squared, that is 0 because of this 0 over here. So this second moment that we have just computed, that is equal to the variance in this case, and that is 2 times tj plus 1 minus tj squared. So we have the variance of these individual terms. We have the expected value of the individual terms. And now we can look at the expression we are aiming at. The expected value of qpn minus t squared. Let's write it out. It is the expected value of the sum j runs from 0 to the number of points in a specific partition, in the nth partition, mn minus 1 of ij squared, right? That is the expression that we would like to get a grip on, that we would like to compute. Now, the first thing we do is we write it out, the square, we write the square out. So that's the expectation of this one squared, plus the cross products, right? We have the cross products, and we have the cross products twice. We have j running and we have I running. So we have a sum, j runs from 0 to mn minus 1 of I sub j squared plus 2 times a sum over I, a sum over j of the expected value of I sub I times I sub j. Now remember that these I sub i's and I sub j's, that these are independent. Yeah, so they are independent. And as a result, we will have that this is equal to the expected value. These are equal to the expected value of I sub I times expectation of I sub j. And we know that each of those is equal to 0, right? So independent. As a result, this term here drops out, cancels out, and the only thing that remains is that the expectation we're looking for is equal to the expected value of the sum. J runs from 0 to mn minus 1 of I sub j squared. And each of these I sub j's, we have computed the expected value. Expectation is linear, so we can swap sum sign and expectation sign. So this is in fact the sum. J runs from 0 to mn minus 1. The sum j runs from 0 to mn minus 1 of that expectation of ij squared. And we have just computed those. Those are 2 times tj plus 1 minus tj squared. So with the sum sign, we end up with the solution, which is 2 times the sum j runs from 0 to mn minus 1 of tj plus 1 minus tj squared. Now we play the same trick as before. We take one of these distances, tj plus 1 minus tj, we take it out, and we estimate it with the maximum distance. So we estimate it with the maximum distance between 2 time points. So as a result, we get a less or equal sign because we estimate it with the maximum distance. What we then get is we have that this expression in total is less or equal to 2 times the mesh, the mesh here, times the sum, j runs from 0 to mn minus 1, of tj plus 1 minus tj. Yeah. And again, this sum we have seen before, this sum is nothing but capital T, right? So it is a telescoping sum. The term that you subtract is the term that you add in a later index, and therefore this is nothing but the final value, capital T. So in total, this is 2 times the mesh, Pn, mesh width, maximum width, mesh width for the nth partition, times T. So in total, we know that this is a square quantity, so it is at least 0. So it is the expression, the expectation of Q Pn minus T squared is always greater or equal to 0, and it is less or equal to 2 times T times this mesh width script Pn that we have just computed. So in total, we were looking at the limit where the mesh width goes to 0 and the number of points go to infinity. So in limit, expected value of Qpn minus T squared is less or equal to limit n goes to infinity, of 2 over 2 times T times this mesh width. And when n goes to infinity, this mesh width goes to 0. And in the end, we will have 0. So we can conclude, based on this proof, that Qpn indeed converges to T in L2. And we write that as the square brackets, a quadratic variation of W with at final time capital T, it's equal to T in L2. So this concludes the end, this concludes the proof that we would like to do here. Please notice again that there's a different proof in the book. And also we have a different proof here in the lecture notes. There's a different proof with an equipartitioning, so a time partitioning that is equidistant, we have always the same time instances, tj plus 1 minus tj, and you can look at that yourself. So we go through those, and essentially this proof goes pretty much in the same way, and we end up with, of course, with the same conclusion. And we have the steps that we take there. It's more, say, the measure theoretical approximation using Chebyshev's inequality and using the Borel-Cantelli lemma. That also gives us the same outcome, the outcome that the quadratic variation converges almost surely in L2 to T, capital T. So let's have a remark here. The remark is the following: the above theorem, the theorem that we have presented and proved, shows that the path of Brownian motion, although they are continuous, they cannot have a continuous derivative. In fact, more is true. The path of Brownian motion are almost surely nowhere differentiable. So they cannot have a continuous derivative, because you remember from one of the earliest remarks that a continuous derivative gives us a quadratic variation of 0. We have a quadratic variation of capital T, so we cannot have a continuous derivative here. Now the second statement, the paths of a Brownian motion are almost surely nowhere differentiable, that is done with another notion, that is done with the notion of variation. So we have the notion of variation. So far we talked about the quadratic variation, and we looked at the quadratic variation, but one can also define the so-called variation of a continuous function. So here we have just the function f again on the interval 0t, mapping values to r, and we know that the variation of a continuous function, and we write it with a v, in order to distinguish it from the var, because the var we use for variance. The variation of f, that is in fact the supremum over a partition, the supremum over a partition of the absolute value of the differences. So the sum k runs from 0 to n minus 1 of ftk plus 1 minus ftk in absolute value. So again, you remember the quadratic variation came with a square, and the variation itself, it is the difference directly in absolute value. And we can write this, of course, again in our more favorable notation with partitions, where the mesh is going to 0 and the number of points is increasing and increasing. So in limit, mesh Pn goes to 0, of the sum, k runs from 0 to the number of points in the partition, and the nth partition, mn minus 1, of that expression in absolute value. Now, a result from analysis, a result from a real analysis, just analysis, says that if a function has so-called bounded variation on an interval 0t, then it is differentiable almost everywhere on 0t. Now, for Brownian motion, one can show, and we are not going to prove it, but we just mention it, one can show that the probability of an event in omega such that in lim sup n to infinity, that w at t plus h for the event omega minus wt over h, we can prove that the probability that this is infinite is equal to 1 for all t larger equal to 0. So here you see a notion of the notion of some notion of difference, right? And in lim sup, this is infinite for all t. The probability is equal to 1. Concluding that Brownian motion is almost surely nowhere differentiable, and hence it has an unbounded total variation. So that is an important notion, right? It gives us the fact that the path of a Brownian motion are almost surely nowhere differentiable. The zigzag curve that we connect to Brownian motion is almost surely nowhere differentiable. That concludes the presentation for today.